Welcome, everyone. Nice to see you all here. Okay, we are good to make a start. So while everyone is just joining us, I can see we've got a few early birds here in the session, which is really nice to see. A couple of new faces as well. So I will just go through a little bit of housekeeping just to let you know how these sessions run. We will start off with the presentation, and then at the end we will have time for some Q&A and discussion. But during the presentation, do let us know where you're watching from in the chat. If you think of any questions during the session, you can put it into the Q&A or in the chat, and I will facilitate those and get those over to our speakers. This session is being recorded and will be available on demand, so keep an eye out in your email inboxes, probably tomorrow, and you'll be able to watch this again. If you are watching this on demand and you have missed your opportunity to ask a question, don't worry, you can either contact myself or one of our speakers, and I'm sure they'll be happy to answer the question for you. So I think we have both of our speakers in here now. So with me, I have Shruti, who is from the Department of Physics at the University of Oxford. And I also have Masilin from the IGAD Climate Prediction and Application Centre. And today they will be discussing with us the topic of cloud-optimised AI-based rainfall forecasting over the Greater Horn of Africa. So I will let you ladies begin, and thank you very much.
Thank you. So I'm just making sure that my sound works. Everyone can hear me. And great. Maslin, is your sound okay as well?
I think it is okay. Am I audible?
Yes.
Okay.
Great. Thank you, Katie, for the introduction. I think we'll start off with Maslin, so I won't speak too much and I'll let Maslin get straight into it with our few intro slides.
Hi, everyone. So today's talk will be talking about issues to do with artificial intelligence and the work that we have been doing over Eastern Africa. So Shruti, you can move to the next slide. Okay, so just a brief background of the region. So this is the area that we are working on. And when we look at East Africa, we can see that most regions are actually arid, and 70% of the population over here depends on agricultural productivity. And then within this area, most people do not have irrigation. So this makes the populations quite vulnerable when we have erratic rainfall over the region. So in a year where we don't have enough rainfall, the livelihoods of the people are greatly affected. And then looking at some of the disasters that have occurred over the region, we can see that we have had quite a number of disasters occurring. So looking from 2009, 2010, we had one of the most severe droughts that actually led to famine over some parts of Eastern Africa. And then in 2015 to 2016, we had one of the strongest El Nino. And then in between up to 2024, we have had quite a number of dry events. And then we have also had excessive flooding. So for example, in the year 2018, there was excessive flooding, and this was mostly driven by tropical cyclones over the region. And then looking at 2019, there was also excessive flooding. And the major cause of this was the positive IOD during that time. And then this excessive flooding also led to the worst ever desert locust outbreak. And then from there, the region experienced drier conditions. And because we had these desert locusts, So it meant that there was not enough pasture in the years when we had drought. And then immediately after this, there were years where we had flooding. So this occurred in OND 2023 and also MAM 2024. And the drought also continued all the way to JJS 2024, where some landslides also occurred over Eastern Africa. So apologies for the noise. I'm in a conference. The
It's
next
okay,
slide.
it's not much.
And then also looking at this project, what we are currently focusing on. So there is a project which we are working on, which is called Strengthening Early Warning Systems for Anticipatory Action. So the aim of this project is to actually use imaging science in terms of producing improved high impact weather forecast. So in this case, we are using the SIGAN for the short range forecast. In terms of outcomes, we have two major outcomes. So one of the outcomes is around data, because of our region, we have quite sparse data sets. So we want to look at other non-traditional weather observations so that it can supplement the station data sets over the region. And then the second outcome looks at how we can produce the high resolution probabilistic weather forecast using machine learning techniques. So the duration of the project is between the 1st of May 2023 all the way to December of 2026. The next slide. So in terms of what we hope to achieve for each year, so we have three major targets. So we are looking at improving the forecast from the short range forecast all the way to the seasonal timescales. So in year one, our major focus was on improving the short range forecast. And then for the year two, we'll be focusing mostly on the short range and also moving towards the 7-day forecast and then also the 14-day forecast. And then when we get to year three, we would like to improve the sub-seasonal forecast and then also the seasonal forecast. So the sub-seasonal range from 2 weeks to about 2 months or a season. And then the sub-seasonal forecasts are from 3 months.
Masilin, I don't know if we can hear you anymore.
Oh, you lost me.
You're back now, yeah. We lost
sorry.
you at 3 months.
Oh, so I had said when you look at the seasonal forecast, you are looking at forecasts that are at 3-month averages, 4-month averages, or also 6-month averages. So you can move to the next slide. And then in terms of the partners within this project, so we have 6 partners. So we have the National Met and Hydrological Services. So within these, we have the Kenya Meteorological Department and then also the Ethiopia Meteorological Institute. And then we also have ICPAC, which is the Regional Climate Center. And then we also have the ECMWF. The World Food Program is mostly doing the coordination and also the vision for the project. And then we have the University of Oxford, where Shruti is, and they are mostly developing the machine learning algorithms and also providing the capacity building to all the other partners within the African institutions. And then we also have Google.org, who are providing the funding and then also the technical and machine learning expertise. The next slide. So in terms of the data sets that we are using, so we are using 6 hourly data sets. So we're producing this at 6-hourly intervals, and the resolution of this is approximately 10 kilometers. For observations, we are using IMAGE, and the major reason why we are using IMAGE is because over the continent, we have a sparse network of observational data. So to train this, we need more data sets. So that's the choice of using IMAGE because it's available at high spatial resolution and also temporal resolution. And then in terms of the forecast, we are using the ECMWF IFS high res. So this is available at 9 kilometers. And the choice of ECMWF high res is because has shown that WF high res well.
I think we lost you again.
Oh, we'll give her a second just to try to reconnect there. Possibly be the Wi-Fi on her end. Oh,
Oh no.
she's
Oops.
dropped out. Oh no.
Gosh. Yeah, I think conference facilities never really have the best Wi-Fi. We can all empathize with that. I'll pick up and then hopefully she can rejoin.
Perfect. Thanks,
But
Shruti.
yeah, so as Masilin was saying, we're really looking at the potential for these cloud-optimized machine learning, and at Oxford particularly, we're developing these machine learning algorithms to, for now, predict from 1 to 14 days into the future over this region that has already had several disasters. So predicting accurate rainfall would be quite good. ECMWF IFS high res is the current forecast that we use to then get to our observational data, which, as Masilin mentioned, is IMERGE. We use 14 input variables. And yeah, ECMWF is the choice here because it's generally shown to represent rainfall quite well over the region. And we forecast with a 30-hour lead time. So that means if you count 30 hours from today, that's 6 a.m. In the next day. As with all machine learning techniques, you have a model and you need to train it over a certain amount of data, and then you also test it on data that it hasn't trained on, just to verify that it's performing well, even when it doesn't see data during its training. So for out of sample data sets, it's still able to have reasonable predictive capacity. We train the model that we use to take this input forecast and post-process them to then correct any structural errors and meet the observational data more accurately using data available from this time range, so 2018 to 2020, and we also test it on 2021 data. The modeling approach follows the philosophy of generalized adversarial networks, and we use a conditional generative adversarial network, which means that, and I'll get to this about what a generative adversarial network is, but bear with me for now and I'll just let you know what we actually put into it first. We have the input forecast variables that I mentioned, and we also have some constants. So we give the model some information on where it is in terms of, land or water, as well as in terms of altitude and elevation. And this goes into a generator that then processes all of this data that's quite high dimensional to then be able to output observed rainfall data. So it's conditioned again on these forecast variables and the land sea mask. And what's nice with these generative adversarial network is that it can output several different predictions conditional on its input data. So it's able to explore what uncertainty you have in what rainfall would correspond to a certain given set of input forecast variables. And with that, you can actually generate probabilistic predictions. which we will also come to later on in the slides about why this is actually quite good, especially for anticipatory action. But now moving on to just give everyone a flavor of what generative adversarial networks actually do in a very simplified manner. What you've got is you've got your generator that, as I said, sort of generates data that corresponds to a given set of conditional input variables. So in our case, the forecast variables. And another component of the generative adversarial networks is the discriminator. And what you do is you say, well, my real data is the rainfall over a certain region, and I want to generate as realistic images. So you tell the generator to try and generate something that's realistic, like the real rainfall data. And at first, it sort of generates a very simple representation of that. And the discriminator is then there to sort of differentiate the two, to say, okay, well, this is obviously generated. And I know that this is the real data, and this doesn't look as close to the real data. So this is generated. And so the generator goes back and tries to come up with something better. And you can see, well, it might not still cut it for the discriminator, until finally it generates something that is very close to what the true values look like, and is able to actually trick the discriminator into believing it's real. And that's sort of the philosophy of how we train these sort of generative neural networks to then be able to generate, in our case, rainfall data conditional on a given set of input forecast variables. So that's just an overview of our model. Currently, the state of the model is that it's able to take in the input IFS forecasts and be able to post-process them to match the observations for the next 24 hours. So if I do it from today, it will be for 6 a.m. tomorrow, accumulated over that time period. So here you can see some examples of the GAN products. We have an ensemble prediction, and we can show the rainfall from that. So you can see here the rainfall over Ethiopia, and this is a particularly heavy rain day. So you can see that there was a lot of rainfall towards the northeast. What's more is that because we've got these probabilistic forecasts, we not only have, let's say, the overall average value of rainfall, but we can also look at the distribution. So we can look at how sure we are about certain values of rainfall over a given point that we prescribe. So for example, here we're showing Waldia in Ethiopia, and you can see the histograms that we then get from our outputs from the generative model. Another example is here over Kenya. This was for 27th of April. This was also a very heavy rainfall day, and a very heavy rainfall day in a series of very heavy rainfall days. So it was overall leading to quite a bit of flooding, especially around Nairobi. So you can see Nairobi's around here, and you can see that we've got the ensemble mean. So we can look at what the expected value of rainfall is based on all of our generated predictions. And we can also look at the standard deviation. So how much spread and uncertainty we have in our predictions. And just as a reference point to the far right, we also have the World Research Forecast, Weather Research Forecast output. And so you can see, well, we don't necessarily always capture the extremes so well with the CGAN, but that's also okay. Another product that we also currently have with the AI model is that we can look at, with the probabilistic forecast, the exceedance thresholds. So this is one of the main key advantages of being able to have these sort of models, is that they're very low cost to run. And typically it's very difficult to generate several different ensemble members that explore the space of what the likelihood is in the future climate based on your initial conditions. And with the GAN, we can actually generate these sort of likelihoods a bit easier with minimum costs. And so we can generate these probabilistic forecasts way easier than what the traditional methods are and also what they need in terms of computational infrastructure. And that allows us to also look at likelihoods of exceedance. So for example, over here, we've got 50 millimeter over a day. That's quite a high level of rainfall to accumulate over a day. Again, this is for the really rainy time, for 27th of April. And we've got the likelihood of exceedance in our 6-hourly forecast. So for the next day, 6 a.m., 12 a.m., 6 p.m. and midnight. And you can see we can get these likelihoods of exceedance based on our probabilistic forecasts that are generated for the CGAD. And this is quite key in actually being able to inform stakeholders about what the likelihood is of seeing a certain severe extreme event occurring so that they can plan in advance. I thought just to put into perspective what the added gain is of our model, so the CGAM, we could actually look at time series for the event period that I've so talked about previously. So from 20th of April to 30th of April, you guys have seen the map of the 27th. And here we're showing the output of the CGAM compared to the output of the initial forecast values that are put in, so from the ECMWF IFS. And these are showing the 24-hour accumulated rainfall. So how much rainfall we forecasted for the next day accumulated over that day. Observations, as given by IMERGE, are also shown in pink dots. And so we're going from the 20th to the 30th of April. And you can see that the CGAN overall is able to have a wider spread in capturing the event, but we still sort of miss out on some extremes. So for example, on the 20th, 23rd and 30th of April, we're not quite there yet. But overall, it seems to be more in range for the CGAN than the IFS. So at least from here, at a blink of an eye, you can notice some improvement. Obviously, to actually properly assess this, we accumulate a lot of statistics over a period of time. And we've also done that. But I thought the case study, at least for this group, would help really put into perspective how you could use the CGAN to generate outputs, especially during severe events. So to sort of hone in on this, I'm going to concentrate a bit more on the 25th to the 30th and go into what we actually predicted on a 6-hourly level, so during the days of these time periods. And here you can again see similar time series, again, CGAN in blue, the IFS, so the forecasts from ECMWF in white, and then the observations with pink dots. But this is again on a 6-hourly level. So going from the 25th to the 30th, accumulated rainfall over the 6-hourly time period. It's interesting to see that you've got quite a distinct diurnal cycle. I'm sure people from the region are aware of this, that usually, especially during the March, April, May time period, you've got a lot of rainfall occurring from 12 to 6 of the day, so from noon to the evening. And that's when most of the activity is. And especially for this, you can see that we do have really improved skill from the CGAN in predicting, especially the noon to evening extreme events. So we're really capturing most of the pink dots, albeit we don't really get some for the very extreme cases. Also, between IFS and CGAN, you can still see that a lot of the body of the distribution is more towards zero. So there is still a bit of a dry bias. And we're not always able to capture extremes with a lot of certainty. So it's always within still the upper tails of the distribution that we're representing them. But one thing I thought would be really interesting to also demonstrate in this is that, as I mentioned before, with the CGAN, you have a very low-cost method of generating ensemble members that allow you to explore the likelihood space of the future weather from a given initial starting point. And that means that we can generate 10 times more ensemble members than IFS with minimal computational costs. What this really means is that we have a better sampling of the uncertainty space, and ultimately we have a better representation of the extremes. So here you can see the results for when we generate 10 times more ensemble members. You can see that we really capture the extremes much better. But albeit there is still some anomalies over there. So it's not all rosy. It's actually, there's some good cases. Most of the time when we accumulate the statistics and look at the improvement compared to the initial ECMWF forecast, there is a reasonable improvement, but there are also some outliers in that. But what this does mean is also that we have a better representation of the uncertainty space, and that allows us to converge towards the expected distribution of the rainfall a bit easier, so that we can also produce warnings. And now I'll come a bit to how and why we would produce warnings from probabilistic forecasts. And I know there's always a lot of issues surrounding communication of probabilistic forecasts, and this is something that needs to definitely be improved. But there is a value, and a very massive added value, in probabilistic forecasts when you're also looking at severe events and trying to generate warnings. And to demonstrate this, I have another case study. So I'm looking at the 20th of April again over Nairobi, and looking at the 24-hour accumulated rainfall. And let's say in this case, we select a threshold of 30 millimeters of rainfall accumulated over the day to mean that there's going to be a lot of activity and some sort of caution needs to be taken. And so this would constitute a bit of a warning. When we look at this, and as any forecaster would know, you would look at the deterministic case and you look at what your weather model has predicted. And if it's predicted more than 30 millimeters, then you would know, okay, there's significant activity. If it's predicted less and it actually was more than 30 millimeters, then you've missed an event. And if it wasn't actually more than 30 millimeters, but you predicted that, then it's a false alarm. And in this case, for the 20th of April, Nairobi, if we use this paradigm, actually looking at the warnings, we would actually have quite a few misses if we only looked at a single ensemble member. So here you can see this area had more than 30 millimeters, and actually most of it was missed. In the case of probabilistic forecasts, you have more flexibility in the decision, because instead of just saying 30 millimeters, you realize that you've got a whole ensemble of predictions. So you've got the likelihood that you will have over 30 millimeters of rain eventually from that ensemble of predictions. And so you can prescribe a certain risk you would like to take with exceeding that threshold. And so let's say that we take that risk as 10%. So if 10% of the ensemble members are showing a value above 30, that is considered significant activity. And if you use this sort of framework, you can see that there are much more hits. There are still a few misses, but also you've got more false alarms. So you are a bit overconfident of this event happening in areas, and then you would act in vain. In the case of 1% likelihood, so when you even lower the amount of risk that you're willing to take with this kind of threshold, and you say, okay, even if 1% of the ensemble members shows a value above 30 millimeters, that's a warning. You still have way more hits. You don't have any misses, but you can see then that you would compromise in terms of false alarms. But this is just an example to give a flavor of where we can actually use probabilistic forecasts as outputted from our IGAD that can be outputted in a very low cost manner to then also properly inform decision-making during severe events. I see Masilin's back, so I'll let her also pick up from there in terms of the benefits and limitations of the model that we've observed so far.
Thank you, Shruti. Sorry, everyone, I got disconnected. So far, in terms of some of the benefits that we see from this is that it's easier to generate more ensemble members. So for example, with the current dynamical systems, it will take quite a lot of hours to just generate one simulation. But looking at utilizing of this machine learning technique, it's easier to generate quite a lot of ensemble members. So we are able to produce a probabilistic forecast at a low computational cost. And then it also improves in terms of the IFS forecast. So looking at the global producing model outputs, once you apply the downscaling techniques, there is actually an improvement, especially in the representation of the rainfall. And then one of the things that is actually emerging in terms of humanitarian organizations, and then also in terms of what WMO is also promoting, issues to do with impact-based forecasting. So with this, it's easier actually to say now, from this forecast, we can see that there's a chance of this high impact event. What is the likelihood of that high impact event occurring? And then these can easily fit into the anticipatory actions where you are setting triggers and thresholds. Once a certain threshold is exceeded, that people know this can actually have an impact on the livelihoods of people, then people can actually act upon that. The only major issue right now is, as Shruti showed in the case study, issues around that when you actually look at extreme events, the SIGAN still has issues in terms of capturing the extreme events. We are still working on this in terms of trying to improve this distribution, and we'll look into techniques that can improve this. So the next slide, please. And then one of the things that we have worked on at IGPAC is developing the visualization website. So this visualizes all the products that are coming out of the project. So here what we can see are some of the products for Ethiopia. And if you look to your, I hope it's the left for everyone, you can see that from this, it actually has different parameters. So you can choose the initialization date where you actually want to see the forecast. And then you can also choose in which units you actually want to see. Is it millimeters per day, millimeters in 6 hours? And then the also good thing is, even though we are looking at 2 pilot countries now, so for now we are working mostly with Ethiopia and also Kenya. But if you go to the area of interest, you can actually see all the other 11 member states of IGPAC. So the forecasts are available, implying that in terms of upscaling, this will be quite easy. And then in terms of the visualization style, it's easier to change from the colors that are currently used within IGPAC to colors that are used also by the member states. And more products are being uploaded. All the plots that Shruti showed, you can also find them from this website. So thank you, everyone, and back to you, Katie.
Many thanks, both of you. Now is the time to ask any questions that you may have. I think we have some hands raised there. So if you would just like to put any questions into the Q&A or the chat, then I will be able to pass them over to our speakers. I can see we have one question from Arthur, or Uther, sorry. Would you mind just retyping that question for us? I think the end of it just got cut off there, and I don't want to make any assumptions as to what your question is asking. So while you do that, I will go to the next question, which asks, what challenges do local meteorological agencies face, do you think, when implementing AI-based forecasts?
Yeah, so I can give like some thoughts in there, and then also Masilin could potentially chip in if I miss anything out. I think overall, actually, there's been a really good reception of it. So at Oxford, there's a really good team of people that really worked well on packaging the AI so it was easily runnable. And so it was very easy to actually, once you've got, the programming environment set up on the laptops of the local meteorologists, like it was very easy to get them to set up the model and run it themselves. And so the forecasts that are generated right now are done by the local meteorologists themselves. So we don't do anything there. One thing that we are trying to do now is the verification, so against what their existing systems provide. And that requires a bit more work. So there is a lot of back and forth that we have to do, but overall the experience has been that people are quite receptive of it. With the AI models, of course, the main computational, heavyweight lifting is done with the training. So that means that you would potentially need a GPU for that. And access to those kind of resources aren't always available for the local meteorologist. But with the IGPAC, we do have access to the Google Cloud platform where we can train the model. So that also has been interesting to set up. And it's also, really good example of where you can really use these kind of networks to be able to get AI and make it accessible on the ground.
Thank you, Shruti. Masilin, do you have anything to add to that at all?
So I think it's mostly what Shruti has talked about, the issues of access to GPU. So the issues around infrastructure, I think it's something that people need to kind of think about, because most of people actually now still have access to CPUs, but not to GPU. So that has been maybe a challenge, and that could be a challenge in the future. And I think one of the other things in terms of NMHs could be the issues of the technical expertise in terms of coding. So there could also be need for capacity building for languages like Python, so that it can smoothly take over and they can also be able to develop their own codes.
Excellent. Thank you, Masilin. So we have the question from Arthur now. So it's actually a two-part question. So I'll go through these questions first, and then I'll come to Saeed as well. So he asks, very interesting outputs. Thanks for sharing this with us. Two quick questions. I note that the IMAG data is at 10 by 10 kilometers spatial resolution, yet the ECMWC IFS HRES is at 9 by 9. So the first question is, how did you handle this variation in spatial resolution to be able to use the data sets together, for example, resample? And the second part of the question was, what is the implication of this spatial variation in the data sets in the validation or uncertainty of the results?
Yeah, so we actually applied a resampling layer within the GAD itself to match the observational data. And of course, you could do also, you could do some pre-processing and regrid it, but we found that when we did the resampling within the GAN itself, so applying this layer, it worked reasonably well and actually was pretty okay, and yeah, easy to run. And then on the second question, how it affected the verification, when we verified, I think we always regridded to the observed data space. So we always did actually verify on the observational data grid. And given that it's just, well, yeah, there's some concerns around that, and you could do it either way, but we didn't really notice much of a discrepancy. So overall, of course, that would add an extra layer of uncertainty, but yeah, I don't think it was so much. But that was at least for comparing, sorry, just to also make sure it's clear, that was for comparing the ECMW of IFS to the observed, because eventually the CGAN always outputs the observational grid. So because you already do the pre-processing, you've got the results or the final results from the CGAN on the observational grid.
Excellent, thank you, Shruti. Masilin, I don't know if you want to comment on that as well, or if would you like me to move on to the next question?
I don't have a comment for this one. We can move on to the next question.
Perfect, thank you. Saeed asks, to which confidence are we going to use the CGAN forecast?
I'm not sure, Masilin, do you want to go first or?
So I
Okay.
can respond to that one. So one of the things that we are working on is in terms of evaluation of the CGAN outputs. So before you start operationalization of any new system, one of the things is to start off with it as a prototype product. So for now, we have started the evaluation of the outputs. And what we have seen now is that it does perform well. The hit rates and the false alarm rates and in an acceptable range for most cases. Where we have problems for now is when we have an extreme event. So let's say if we experience rainfall, maybe that is above 100 millimeters, because maybe some of these events have not been seen in the past, then it might be also be difficult for the technique to produce this. But we are working on improving this, and once it's improved and we have confidence of it having appropriate early warning system, then this will become operational and we'll be using it with high confidence.
Brilliant, thank you, Masilin. The next question I'll go to asks, how do you envision scaling this initiative to other regions affected by climate extremes?
Perhaps Maslin should. I think she's more involved in like the regional activities and communications.
So I think that is a twofold question. So other regions could imply the regions within the IGAD region, and then also outside the IGAD region. So in terms of within the IGAD region, we are already trying to upscale these initiatives. So in the upcoming year, we are planning to have capacity building workshops for the member states, where we also train them on what we have done. And I think also, to my understanding, there are quite a number of countries that are quite interested in these techniques outside the African continent. And I will double check on this, but I think there are already some countries which have actually started to adopt some of the techniques that we are working on. So for at least within the IGAD region, we plan to engage the NMHs and also impact some of these techniques to them.
That's excellent. And I guess following on from that, how are the communities trained or equipped to act upon the improved early warnings? Is there a difference in that communication?
So Katie, that is a very interesting question in terms of then how do communities uptake this information. So one of the things that we have realized most of the times as climate scientists, we are not the best people to actually downscale this information all the way to the last mile user. So one of the things that we have really worked on is to have a communications team that actually packages this information in a way that it can easily be uptake. And then also in the past, we have trained quite a number of journalists, because the journalists are able to write this in a way that it's easier for people to understand. So those are some of the initiatives that we are working on in order to have to increase the uptake of this information. And I think, as Shruti has said, this is probabilistic information at daily timescales, and people have actually been more used to deterministic forecast. So there will really be need for us to capacity build people in terms of uptaking these new probabilistic forecast at short range timescales. Yeah.
No, that's interesting to know. And what are your next plans or next steps for this initiative?
So I can go first on Oxford side, and then let Masilin also take over on that for the IGPAC side. At Oxford, we're also looking into other different models. So we've currently got a GAN, but there's obviously a whole suite of other models that have come out since then. So we are exploring, for example, diffusion models. We're looking at what the effects are of the training time period on what your model performance and ability to represent a certain diversity of outputs is. And we're also trying to, perhaps in the long range, once also the observational data is a bit more thoroughly checked, as Masilin mentioned in the, I think, second slide, that one of the outcomes is also looking at the observational data sets, also seeing if we can integrate non-traditional ones. Once we've got that kind of data, being able to maybe assimilate better quality data, because right now we use iMerge, but obviously it's not the best for representing extremes. On the other side, we're also trying to really directly link certain rainfall amounts to impacts. So, for example, we're looking at this Nairobi case study and looking at the urban flooding events and seeing what levels of rainfall can have what impacts, so that we can also directly translate these to probabilistic triggers. But that's, again, a work in progress. And yeah, on the IGPAC side, I'll let Masilin continue.
So to just add on to that, in terms of impacts, I think one of our biggest worries is preventing disasters from happening. So for now, we are mostly focusing on rainfall, but would also like to look at issues of cascading events or multi-hazards, where we actually say, like, rainfall sometimes over our region. When we have heavy rainfall, we can end up with landslides, mudslides. So those are some of the issues that we want to take this work further to actually see if we can actually be able to focus some of these impacts that cause a lot of damage over the region. And one also other thing we're looking at, or we're discussing, issues of vegetation condition indices. So trying to use the outputs from this and the techniques to also do vegetation condition indices. The other thing we were looking at is, can these outputs from SIGAN be used to drive hydrological models? Because in hydrology, they really do require a lot of rainfall outputs for rainfall data, and then they use this to drive their models. And usually they want it at higher resolution than we can normally produce. So with this, because it's producing, the frequency of producing the output is much higher, so it might also be easier to drive the hydrological models using outputs from SIGAN. Back to you, Katie.
Thank you, Masilin. We have another question from Amal, who says, concerning the computation capacity, are the computation resources from google.org, will they be available for the IGAD state member countries after the project completion?
So currently we do have quite a few cloud credits to train the model on, but I'm not entirely sure what the outlook of that is. There is, and I'll let Masilin actually pick up from here, I think plans for sustainability of the project once it's over. So perhaps Masilin can also pick up from here.
Yes, so that's a very interesting question. So from right at the beginning of the project, Google also wanted us to develop the sustainability plan, especially for the cloud computing resources. So we are working on that sustainability plan because definitely we still need to continue with producing this. And as usual, would also like to have our member states have access to the computational facilities, because for now they have access to our infrastructure in terms of the high performance computing system. So we want to maintain this, and we are working on the sustainability plan after this project.
Excellent, that's good to know. Do we have any further questions? I'll give you some time just to type any out. As I mentioned, this is being recorded, so if you would like to go back and rewatch it, you should be able to. We'll be able to send the recording out to all of your email inboxes probably by tomorrow. Ignacio says, thank you very much. Very interesting topic. So that's good to know. If you do have any questions or you think of something later on, do reach out to our speakers there. I'm sure they'll be more than happy to answer your questions. I can't see any further questions, so I will leave it there. I want to say thank you very much, Masilin and Shruti, especially bearing with us. I know technical issues can be such a pain sometimes, but it is what it is. We're just very happy to have you here to share the initiative. So thank you very much, and thank you everyone for attending.
Yeah, thank you.